Nadia, are you saying something about the reactor at the start or at the end?
I'll do it at the end.
Okay, cool. Can you see my screen?
I can see your screen, Paul.
Cool. All right, guys. Thanks to everyone for joining us this evening. We're lucky enough to have James Ward, who I met surreptitiously through running a Bayesian course also at the Microsoft. Reached out to me, and we had a meeting here in Maroubra, and met up and talked about, I guess, causal science, and it was a really fascinating talk. And James and I have continued to be in contact since. But through that, like, I suggested to James, hey, would you like to give a talk on this? And he's lucky enough agreed to that. So he's going to be presenting on causal inference, specifically causal science, I guess, more specifically. And that's I guess the theme for tonight. I'll just quickly say a few things about myself and provide some resources, and then we'll hand over to James. So my name is Paul. If you haven't met me through one of these meetups yet, I run Sydney Machine Learning and DSAI. If you would like to find me, you can find me on Twitter at that address. I usually am tweeting about all things machine learning related, but at the moment there's a few COVID things there. I'm not gonna lie, but for finding out and staying in touch with like the latest developments and trends in this field, because it's such a rapidly evolving field to be in. And I guess if you follow just specific machine learning researchers, you can get it's a lot of value out of it, as opposed to getting a lot of noise. I also run the Humans of AI podcast. Just going to quickly plug this because an episode came out. I released an episode last week, and I think it's valuable for anyone that's thinking about being a data scientist or anyone that's practicing to have a listen. So in this episode, I interviewed Damien Brady, who is a dev ML ops advocate slash practitioner at Microsoft. And we sort of talk about the new and emerging field of machine learning operations. So that's like the best practices of taking a machine learning model solution all the way from like Genesis, from like, how you kick the project off, all the way through to putting that's very valuable. Machine learning has kind of been the Wild West for quite a while, and now it's beginning to formalize. And MLOps is that field to pay attention to. Right. So just to sort of preface this, James is going to go into. He's going to cover sort of a high level tonight, and then also do a little bit of a deep dive. But he'll be saying more about that in a minute. But yeah, just to sort of preface, if anyone's interested in sort of learning more about this after this talk, there's obviously, if you haven't read it already, the Book of Why by Udaya Pearl. I probably should have added that to this list, but it's a really good read. If you haven't read it already, please do. It's probably will change your idea on how to do science. And I'm not kidding. It's kind of that kind of a big deal. But if you want to do some practical examples, here's a couple of things to go through. So first is this excellent lecture, which I just only recently found on YouTube. The link is called Causal Inference in Machine Learning and AI. That's the actual of the lecture, and I'll just move my mouse out of the way, and hopefully you can get that link there. Cool. Leave that up if you want to take a print screen just for five more seconds. The next resource is this Udemy course, which is made by the same guy. And I'll just say something like, I haven't been paid by anyone or anything to say this, but I just think it's like really cool to do practical examples to learn something. That's just like how James was saying this before. Like when it comes to learning, it really pays to. Everyone's learning style is different. For me, I like to learn through exercises. So if you want to do exercises too, this is like a really brand new course that's been released on Udemy, and we'll be doing a study group around this with DSAI in the coming months once everything settles down. And then, just want to say something there. So just a little bit of intro around James. But there's two parts to this talk. So there's, and James is going to say, explain this now, but just so that you're aware, the first part is going to be sort of a high-level overview of this field, if you haven't heard anything about it. And then the second part is going to be more of building a theoretical foundation. So there's the idea being is there's a bit of content for sort of everyone here. And yeah, with that being said, I'd like to hand it over to you, James. So yeah, cheers, mate.
Okay, great. Well, thanks so much for the introduction, Paul.
The post you shared on Urumi?
I'll share the links via chat now, but yeah, just yeah, handing over to James.
Okay, I'll just wait 2 beats for anyone to ask a question of Paul if they'd like to, and then otherwise we'll kick off with the session proper. So first of all, I'm so pleased that so many people joined the call, and I think that it's exciting for a number of reasons. One of them is I'm very excited to be speaking to so many data scientists, but I know too that all of us aren't only data scientists, we're also people, and we care about the world, we care about what happens in the world. And so we're very much tied together in the sense that we all share the same future, and we'd all like that future to be better. And to me, causal science is the way we make that future better. And so thank you very much for contributing to our joint project of making a better future. So here's our course outline. As Paul mentioned, we're going to be running this in 2 parts. The first is for a general audience, where what we're doing is we're setting up the reason that we care about the topic. And so our topic is going to be intelligence generally. And some people can see this as a very abstract area of discussion. Today, we're going to make it very concrete, and we're going to show why it's important that we give this our full attention, both personally and professionally. We'll be outlining a number of problems in the domain of intelligence. And having set those up, we're going to use part 2 to then show how something called causal science addresses all of the problems that we introduce in part 1. So that's the overall structure of the talk. And so to kind of break that down just a little more, we've got the primary topic of intelligence, and we're going to be tackling it in these ways. First, we'll look at intelligence.
Just a heads up, James, your presentation hasn't been shared at the moment. So just if you want to share your screen.
Oh, it's not being shared. Okay, let me just get that shared. Okay, how are we doing?
Yeah, that's great. It's up.
Got that. Okay, good. I'll just get my Teams window back in the front. And so what we're seeing here is the outline of the talk. And so we'll be looking at intelligence as our primary topic, and we'll be stepping through exploring that in at least 4 ways. The first is anecdotally. So we'll be telling anecdotes about intelligence, what it means to the lay person, moving on to what it means to experimental psychologists. Then we'll get into formal definitions of intelligence, and finally we'll look at how we actually compute things that are intelligent. So that's really where the rubber meets the road. When we get computational about this, it's very easy to speak about intelligence in a kind of arm-wavy way, and you kind of have to start there because we've got to introduce the topic, we've got to introduce the problems. But I want everyone to rest assured that where this is all headed is toward the ability to actually write software that is intelligent, which is an enormously big call, and it's really the defining scientific achievement of our era, that we're on the cusp of making this dream come true. And so that's really the ground we're going to explore tonight, the connection between intelligence as a concept and then taking it all the way through to a computational reality. So we've only got 2 hours. We're going to make the most of it. But what I'm hoping is not that this is an enclosed, self-contained lecture with start and finish. I'm hoping it's just the beginning of a longer conversation which starts here on this stream and then continues afterward in a number of forums. So I know that whether that might be email exchanges, or it might be additional meetups or lecture series or tutorials or whatever that form might take. So I think the right place to begin to address this enormously large and hairy topic is to first begin with the question, why is talking about it so hard? Because probably you've never spoken about intelligence in the way we're about to today. And it's worth pausing to reflect why that is. And then once we've understood what the roadblocks are to talking about it correctly, we'll also be looking at why it's also so essential to have that conversation. So two things there. It's a really hard conversation to have, but it's so essential that we have it. And so let's make sure we understand and cover both those points correctly and properly at the depth that they deserve. And I've shared my email address with everybody, and I'm doing that repeatedly because I do encourage this continued dialogue so we can really burrow down on this and get all of our questions answered. Now, tonight I'm going to be talking about all kinds of things. You'll be surprised at the range of things we address. And along the way, we're going to be pointing out a whole bunch of problems. And the promise I want to make right at the start is to say that every problem we raise has a solution. And when I say a solution, I mean a technical, methodological, and technical solution. And it's going to take a while to get there, but the promise is that that's waiting at the end of the rainbow if we can just have the patience to learn and the discipline to apply what we've learned. So step number one, the roadblocks. And so here's the first thing. Mostly when people talk about intelligence, they come at it through the lens of psychology. This is historically how intelligence has been thought of, how it's been positioned in the psyche of humanity. And so psychology began in sort of 1800s, and it explored all of those things that we see there on the slide, the axiology, the epistemology, ontology, semiology, and it did it through the tools that were available to psychologists. And when psychology originally began, that primary tool for that was the couch. And so, you'd lie down, the psychologist would chat to you, he would have his method for arriving at all kinds of conclusions about your psychology, one part of which is your intelligence, and then he would perform diagnoses, treatments, prescriptions, and nurse you back to mental health if that's what's needed. Now, the giants of the field are guys like Jung and Freud, and these guys were into the subconscious. And because of that, the idea of intelligence has sort of become a little bit connected with something that I think people call woo. So, W-O-O. So that's a word to refer to things that aren't very precisely defined. And when we have words that aren't very precisely defined, all kinds of charlatans can rush to fill the space and create explanations for phenomena that are frankly unscientific. So that's one of the problems with approaching this from a psychological perspective. So there's the idea that it's kind of well-trodden grounds, there's nothing new here, the idea that the existing set of tools are enough, and then finally the idea that really psychology is about understanding intelligence and the mechanisms of the mind. It's not about creating intelligence, and that's really what we want to do. So if we flick to neuroscience and see how they approach the question, we've got a new set of issues. And the primary issue here is that intelligence is seen as the product of a brain, and a brain is a physical thing. And so the idea is if we're looking for intelligence, we should look at the brain. And so what neuroscientists do is they slice open brains and they start looking for intelligence there. And of course, this is a very shallow way to view intelligence. And you see that all of these things that are active in psychology are suddenly missing when we take a neuroscience lens on the problem. And instead, we're looking at brain cells and EMG scans and all of this kind of physical activity, which is measurable, but doesn't hold the keys to what intelligence is. So if we were going to take a kind of correct, proper scientific perspective on understanding intelligence, we'd like to be measurable. And we would like to be able to measure intelligence so we know it when we see it. And so let's imagine trying to create some kind of scale against which we can say, well, you know, over here we're measuring 10 watts of intelligence, and over here we're measuring 20 watts of intelligence. And then we'd at least have some way of understanding when we were creating something that was more intelligent, or encountering something that's more intelligent or less intelligent. And then we can start to create hypotheses in the space. Now, of course, this scale's been invented, and it happens to be a terribly controversial scale. It's the IQ scale, and it's fallen out of fashion. And the reason it's fallen out of fashion is that this scale of deciding where people fall on an intelligence spectrum was first used by the practitioners of eugenics. So the idea of eugenics is that intelligence has a genetic cause. And so Galton was the first guy to sort of run with this idea and take a scientific approach to it. And he became one of history's famous eugenicists. And the problem with that, especially through the lens of today's cultural mores, is that as soon as we use the word genetics, we're using the word race. And so imagine, if you will, overlaying on top of my picture here the idea that your intelligence is racial. And of course, this is a horrifying idea to anybody who sees that it's very essential that there's no kind of supremacist race. One race isn't ascendant over another race. And so because of this horrified reaction to the idea of measuring the intelligence, and that the intelligence was genetic and therefore racial, and that we were actually going to measure these intelligences against each other, the ethicists jumped in and said, you can't do this. This is off limits. We are not allowed to talk about intelligence in this way. And by the way, because of our ideology, you don't need to measure it because everybody's equally intelligent. And so, you know, that was good in a way because it kind of shut down any racists who wanted to push supremacist theories, but it did very much rail against the idea of having any sort of scientific inquiry into what intelligence really is and how it might be built and so on. So the other idea that came from the ethics perspective was that if any differences in intelligence did exist, they were only due to external factors. And so so they're the product of wealth or the school you went to or the opportunities you've had. And the trouble with making that assumption is it kind of begs the question. If you want to ask, where does intelligence come from? And you already have an ideology that's supplying all of the answers, well, this isn't scientific inquiry. And so this is the problem with this approach, that you already know the answers. So the eugenicists made the error of assuming everything was genetic, and the ethicists are making the mistake of assuming a priori, that's before doing any investigation, that everything is environmental and cultural. And so both of those things shut down inquiry. And so what's happened is we've sort of landed at this state of artificial intelligence where we kind of get the humans off the scale and we say, well, here's the way to solve this problem. We can measure the intelligence of artificial intelligence, that's fine, and we'll just assume that all people are equally intelligent and that they represent the pinnacle of intelligence. And so you can see how this is kind of a really neat solution to the problems seen by the ethicists, and everybody's happy. So this has kind of become the cultural norm. And it's also been strongly supported, this idea, by Alan Turing. Now, Alan Turing kind of pranked us all and came up with something he called the Turing test. It was later named the Turing test. And the idea was, if there's a robot that can convince you it's human, then that's the proof that it's intelligent. And so just let's pause and have a think about what this means. The test of intelligence currently is that we're able to mimic humans, you see? And you might think that's safe enough. What's the problem with that? But here's the problem, that we've kind of constructed this social consensus on intelligence and on AI, and it's defined an Overton window. Now, the Overton window, for those who aren't familiar with that term, is it describes the set of things you're allowed to talk about. And what we're allowed to talk about is that there's this thing called real intelligence, which people have, and then there's this other thing which tries to mimic that. And so because it's mimicking that, it's not real intelligence, it's artificial intelligence. And so this is okay. If you go into a science class or into an ethics meeting or into a business meeting and you have this view of artificial intelligence and intelligence generally, then you'll get a big tick, and this is inside the Overton window, and nobody has a problem. And we see this idea showing up everywhere that AI is being developed. So if you go, for example, to Microsoft and we have a look at their AI offerings, this is what we find. We find we've got Angel Eyes here, which mimics human vision and the kinds of things a human would care about. We're looking at a maybe and so on. We've got Clean Water AI, which is mimicking human taste and saying, well, is this water safe for humans to drink? Does it have bacteria? And that's kind of the thing that is championed most strongly today, is anything that says, hey, look, AI can do what humans can do. And that's why everybody's going nuts right now for NLP, because NLP means natural language processing with a heavy emphasis on the word natural, right? Because what does natural mean? Natural means, well, humans do it, right? So if we can process language the way humans do, well, then this has got to be the pinnacle of AI. And so we see this in Siri and Alexa, and it's kind of everywhere. And I think this meme, which I ran across, really captures the current state of AI today. And I'll just give you a moment to take this in, what this is really saying. And it's kind of spoofing the idea that we've got this robot, Sophia, and the measure of her quality as an AI robot is how well she can participate as a human, be a human, have a baby like a human, etc. And so I think this is kind of a hilarious takedown of this style of thinking. But what's been left out of this picture that is so important? Something's missing, and the most important thing is missing. And here it is. It's the idea that artificial intelligence can be much, much more intelligent than people. That's what's missing. This is what's outside the Overton window currently. And so there's plenty of forums where if you run this idea, then you're going to get a lot of pushback. You're going to get a lot of ridicule. People say that's impossible, or you're talking about AGI, we can't do that. Nobody's smarter than people. But of course, it's very easy to push back on anybody who makes that representation, because really there's nothing left, there's no problems left anymore, whether it's chess or playing computer games or playing Jeopardy. There's really no realm where AI isn't dominant. So my advice would be to let go of the idea that AI is a human-centric thing, and to start thinking about intelligence as something that exists independently of humanity. And I know that's a lot to take on, but unless we do that, we'll never create intelligences that exceed what humans are capable of. And that's really what we'd like to do. And it's kind of curious that we have this perspective on artificial intelligence and humans and so on. Because if we take this sort of sideways into the physical space, we say, well, mankind's a tool-building animal, and we're strong, but when we want to be stronger, well, we use a crane, we use a tractor, we use a forklift. And this is how we build our modern industrial environment, all of our infrastructure and our planes and our rocket ships and our skyscrapers, and we couldn't do that otherwise. So why is it so different to say, well, why don't we delegate the intelligence task, the task of thinking problems through, to machines? Because they're much better at it than we are, and we'll get much better results, and we'll all be better off. Just in the same way as we say, well, let's not limit our physical carrying capacity to what we can do personally, well, let's too not limit our intellectual carrying capacity by saying, well, only humans can do this job. And of course, there are those who will jump in and say, oh, but think about the risks. And just as you would, you'd say, well, that crane could kill a small child, or that crane is, you know, that you could talk about all of the negative things. But certainly in the physical world, we've decided that the positives outweigh the negatives. And that's so much more true in the realm of intelligence. If we could only be more intelligent, then so many problems which seem insurmountable today would become soluble. And in fact, it's exactly what's happening when people take the view that AI is able to outperform people. And so the result is that although we've got this great expanse of space to explore, everybody's stuck down here in this little circle, and it's a problem for everybody. And I'll explain why. The first is that, let's start with the business community. So the business community looks at this picture and says, oh, look at those AI people. They're trying to create artificial humans. And while that's kind of a cute little science project, it's got no relevance to my business. And the reason is that I can already hire humans at $15 an hour. And so if I want human capabilities, I just go and hire one. And this has been true since cavemen first invented the wheel. And so really artificial intelligence, it's kind of cute and everything, but it doesn't change my work, is how a businessman looks at this. And this is a great shame for data scientists, because to sort of flip over to the data science community, I think most of them are working on what I'd call the wrong problem. And the right problem is how do we get more intelligent? And the wrong problem is how do we mimic humans? And I think too many of us, some of us have to do that. And I think there's been some enormous advances in machine vision and natural language understanding. There's certainly a place for that, but that's where most of the ground that we have made in artificial intelligence, that's where most of the goals have been kicked. And it's time to go kick them somewhere else. And so if you're a data scientist looking at the right problem to focus on the problem of being smarter than people, not mimicking people. And then what that will do is it will give the business community something to be interested in, because now we're offering something that they can't get from their workforce. Now we've got some real value to add. And so this is what I encourage us all to look towards. And then so too the political community. So the political community is constantly pointing out all these problems. We've got global warming, and we've got COVID, and we've got all these challenges. We've got hunger, and we've got famine, and we've got trade, and we've got the trade war and South China and all of these things. And if only we could apply superior intelligence to reasoning through our options and our best strategies, then we'd all be better off. And so that's really where we should be. This is where the opportunities lie. And so we want to investigate all of these subjects, axiology, epistemology, ontology, semiology, through the lens of AI, not through the lens of people. And we want to use it to really kick goals. And so I myself am working on software that does exactly this, and plenty of other people are too, and we'll talk about the field more broadly later in the session. But just to explain where this talk really comes from, it comes from somebody who is building software with this goal in mind. And so the software that does this is called Sky, and it's very firmly grounded in causal science. And so the way to understand Sky and this entire space is to first of all understand causal science, and then we'll understand then how it can be turned into software that can be used by business people and politicians and policymakers and strategists and doctors and medical people and econometricians and everybody else. Now, of course, Microsoft is one of the companies that has rolled up their sleeves, and they're dropping $1 billion on this. They're spending $1 billion to make AI that's better than humans at everything. And so this can be immensely controversial. in some quarters. And so there's a number of opposition groups that have sprung up in the face of this and said, well, you know, we need an ethics committee and we need to ring fence AI, and AI is going to kill us all. And so there's tremendous opposition to this idea. And one of the questions that I think we need to, that's an important discussion to have, and we'll have that on another day. But just for now, I'll just point out that that opposition does exist. But if we want to have a look at what an ideal future looks like, then here's the picture I would paint. I'd say we've got the ability to use causal science to build software like Sky, and then also offerings from Microsoft and other places, and then offer intelligence as a service to the world. And that can then be used by policymakers and green groups and everybody who wants to think through what they should, which strategies they should use to achieve all of their goals. So let's do that. Let's put ourselves in the position of a user of intelligence and say, well, what's it good for? Like, imagine that it was possible to build this, you know, smart machine. Who would use it? What would be the value of creating it? Is this just some kind of vanity experiment for scientists, or is it actually the most important and worthwhile thing we should be spending our time on? And I would argue that it's the latter, of course. So who are the people who would be using this? Well, it's the Australian government, you know, because they claim that evidence-based policy making is very important to them, and they've got a number of very important problems to solve. Right now we're looking at the lockdown problem, then we're going to have the economy restart problem, we're going to have the aging population problem, we've got the housing problem, so many problems. And we'd really like to look at this with intelligence. And let's make sure that that happens. Now, you can read on their website about how it's actually really challenging to do this thing called evidence-based policymaking, and it certainly is. And they're not the only ones who've noticed that. So here's another group, the Effective Altruism Project, and they're all about saying, well, when we deal with charities and we're taking money from people to create good in the world, let's not only do the things which feel good in the moment. Let's actually reason through the cause and effect change, so that if we spend money here or give money or subsidize this or make this free or nationalize something, that we think the problem all the way through, and then we can judge the merit of actions based on their eventual effects and not on how good they make us feel in the moment. And that's really what the effective altruism movement is all about. So that's something else you might want to check out after the talk. And then you've got guys like the Lifeboat Foundation, which they're constructing something called AI Shield, which is basically, you know, a way to ring fence AI and stop it killing us all. So that's what they're all about. But have they thought through the implications of what they're doing? So they claim to be acting in the best interest of humanity. Is that really true? Well, to address that question, you'd really need to bring a lot of intelligence to bear. And so we would encourage them to access the highest form of intelligence available when they're making that determination. So another one is looking at, say, energy policy, if we were going to get more specific. And so Shell is someone who looks at the future of green energy and oil and coal and does all the trade-offs. And they do this through something called Shell scenarios. So I'm going to play a little clip. I'm not sure how our audio will be, but let's see how we go, because it just kind of describes the way they go about the problem.
There's no audio at all, James.
Oh, okay. All right, so no audio on that. But essentially what we're looking at is a process that they run where they ask what if questions, and then they've got a complex way of getting people together to look at these big issues. And essentially their process boils down to this. They ask, what will the future be like? and they involve experts who then talk about the future and then come up with scenarios about what the future would be like, and therefore what are good things to do. And so here's really their model of what good looks like. We get a bunch of people together, and now we've got human collective intelligence, and we go and solve the problems. So let's then examine, in the light of that, if this is a good idea. It's a good idea if the people are reasoning correctly about cause and effect. So meaning, if they're presented with some data, are they able to say, oh, I see what's happening here, this causes this, causes this, causes this, and so if I take this action, this will be the effect in the future. If they're doing that correctly, then this is a great model, but if they're not doing it correctly, it's very dangerous, because obviously they'll be making the wrong decisions. So why don't we have a look at how people reason about cause and effect? And there are all kinds of scientific experiments that have been done in this realm. This one by John C. Wright. And he does this. He says, let's set up a poker machine. You've got to kind of press buttons on the outside, and you've got to figure out what will cause the machine to pay out. And so let's try this one. Let's select only sets of even numbers like this. And no, no payout, didn't work. All right, so let's try something else. Let's select only sets of numbers where no number is divisible by any of the others. So that's our rule. We think that's going to cause the machine to pay out. We try it, and it does. Okay, that rule works. And so can you imagine continuing to do this for 323 more times, so 325 times, and trying to determine what rule makes the machine pay out? Now, when this is done experimentally, here are the results of that experiment. So the thing is, the test isn't as it seemed, of course. It's a psychology experiment, so we all knew that there was going to be a surprise coming. And the thing is, there is no causal rule. There is no causal relationship between the rules that the people are imagining and the payout apparatus of the machine. It's all random. And so what's surprising about that is that when the participants are told this, they don't believe it. And they can't be shaken out of their belief that they have unlocked the true causal pattern of the payout mechanism of this machine. And so that's kind of frightening when we know for sure that causal relationships don't exist, and yet we've got people who have been told this is an experiment and you've been punked, and they're still refusing to believe that that's the case. But maybe appointed industry experts are going to do a better job. So let's think about that. So Bloomberg, they're professionals. Then what they do is they report on stock markets and the things that are driving the stock market. And so here we've got an example. Saddam Hussein's captured by US forces, and so US treasuries move higher. And so they publish a headline, which is US treasuries rise. Hussein capture may not curb terrorism. Okay, so there's a cause and effect there. It's very clear. The only trouble is that soon after they published that, US treasuries moved lower. But no problem for Bloomberg. They just adjusted their headline and they said, well, clearly what's happened is US treasuries have fallen because Hussein's capture boosts the allure of risky assets. So this is new causal reasoning. But what they really should have published is something like this headline, which is US treasuries fluctuate as they always do because Saddam Hussein's capture has nothing what to do with yields whatsoever. But, obviously no one's ever this honest. And Danny Kahneman speaks about this, and he says that when journalists write, very often, and this is true, I'm not picking only on journalists here, but so many groups of professionals ascribe cause and effect where it's non-existent. And they do that because people are so hungry for cause and effect kind of relationships. There's also kind of the politics to take into account. So this is the famous conformity test, the Asch conformity test. And in this one, people are pulled into a room and they said, okay, we've got this line on the left. Which line on the right is most similar? And so I can see by eye here that line C is similar. But would you think it would be possible to convince people to answer incorrectly? Well, it turns out it's surprisingly easy. And the way they do it is they put actors in the room. They ask the actors the question first. They say, which line is most like the one on the left? And the actors all say line A, line A, line A, line A. And then you ask the experiment subject, and these are the surprising results. 75% of people conform to whatever answer the actors gave, even though it's clearly not true. And so this is horrifying, because what it means is we don't have our brains engaged, particularly when we're in social environments and we're reasoning about causality. And we see this conformity cropping up all over the place. There's a very entertaining commercial doing the rounds, which I don't think we've got time to show, which really shows how all of the ads that are being produced these days are all exactly the same. And in a field where we would expect a lot of creativity and diversity, we're finding instead a lot of homogeneity and conformity. And so are these the only kinds of biases? Well, no, there's thousands of them, and humans are steeped in all of them, and they're all happening at once. So this is a big problem. Now, most people will tell you that they're evidence-driven. And so, okay, let's try and take that seriously. And but one of the immediate problems we run into is that most data available to people is just simply fake. And so here we've got Ellen Powell, former CEO of Reddit, and so she's an insider. She knows what's going on the inside. And she's admitting publicly here in a tweet that the numbers are fake, the metrics are fake, the content's fake, the people are fake. And so anyone trying to get a picture of the world by looking at things that are published is going to be sorely misled, unfortunately. And so one of the kind of great examples of this is to show video of this, which is a Chinese click farm. So in this Chinese click farm, we've got physical iPhones that are strapped to walls, and they're all downloading apps, and they're liking things on Facebook, and they're doing things. And people can pay to be liked, and they can pay to have their articles read, and they can pay to have their apps downloaded. And of course, none of it is real, but it makes the metrics seem really good. Now, a lot of people will tell you, hey, I'm wise to this. I'm wise to this. I know the internet's all fake, but that's okay because I rely on credible sources. And so I said, okay, tell me about your credible sources. And, so for example, journalists who are in mainstream publications. So here's an example. I thought, how far have we got to look for an example of where people probably put just a little bit too much trust in somebody else's causal description of the world, and or somebody's representation of what reality is. So here we've got Stephen telling us about the share market, and I'm sure that when he's saying this, I'm sure that he believes it. Share markets are ignoring the economic devastation the pandemic is wreaking. And so, we can sort of find this repeated closer to home. Now, this particular journalist is quoting somebody else, and I'm sure when he's saying that Australia's share market has staged a full recovery, I'm sure he believes it because he trusts his credible source. Now, the credible source is named here as UBS. And so I'm sure that the spokesperson at UBS also relied on credible sources and so on. But it doesn't take much digging to sort of go straight to data and question this. Has Australia's share market staged a full recovery? I mean, this graph would suggest not. And so we must really pause and think, how many of us believe things on the basis of a credible person having told us? And if then ever some misinterpretations of the data enter the stream of interpersonal communication at some point, it can be very difficult to check bad information being disseminated. And so without there even being any bad actors in the scenario, nobody's doing anything intentional. There's no intentional lying going on, but there's just a reliance on so-called credible sources, like in the way Dominique here relied on his contact at UBS to know that Australia's share market had staged a full recovery. And so then we've got, sort of influences on the media landscape. So Facebook now pay for news. And so, of course, demand will create its own supply. And so if Facebook prefers a particular type of story, economics will determine that suddenly people will spring up to supply whatever type of news Facebook wants to buy. And so even though there's no conscious biasing going on, we still have to be aware of how biases can enter the system nonetheless. And even without saying anything that's factually incorrect, it's still possible to misrepresent some characteristic of our reality. So here, water's being positioned as something intensely dangerous when you and me know that that's not the case. And so some people will come at this and they'll say, well, obviously we need to go straight to the data and we need to use our correlation or machine learning to set this all straight. And if we go straight to the data, we'll have no problem. And so here's an example of a graph where we say, all right, here's a very clear example. We've run a regression through this. And as exercise increases, cholesterol increases. So clearly more exercise causes higher cholesterol. Who could argue with that, looking at the data? Certainly not Homer Simpson, he loves it. And then we say, why don't we striate this data by age group? And we see the famous Simpson's paradox, and we see that once we separate all of these data points by age group, in any one age group, the relationship between cholesterol and exercise is actually reversed. And the more exercise that you do, the less cholesterol you have. And so this is a big problem for Homer because he thought he could sit on the couch and exercise less to get his cholesterol down, but now he knows that exercise combats higher cholesterol. But hang on a second, then so why does the age cohort, if that's true, if exercise combats higher cholesterol, why does the age cohort doing the most exercise have the most cholesterol? It doesn't answer that. So we thought we had an answer, but actually we've just fallen foul again. And we've seen that this is an oxymoronic thinking. And so we've got to look for other ways to interpret the data. So maybe it's that older people exercise more and people with higher cholesterol exercise less. And so now we've got something that fits the data. But hang on. So then if the old people exercise more, if they're the ones with higher cholesterol and people with higher cholesterol are supposed to exercise less, once again, we thought we had an answer and we really don't. But maybe this is it. Maybe older people have higher cholesterol and people with higher cholesterol exercise less. But hang on. So shouldn't older people exercise less then, since they've got more cholesterol? And you see, you can just go round and round in circles. It's actually intensely difficult to make coherent causal explanations of data sets. And this is us as people doing it, never mind trying to run very simplistic regression algorithms and so on across these things. And even if we give ourselves the kind of the liberty of using Bayesian networks and these kinds of representation systems, as we're seeing here, this represents a DAG, a directed acyclic graph, which is very intimately connected with causal science. We see that we still run into problems. Okay, older people have high cholesterol. Like, is this the answer? And we discover that there's these oxymorons. So we've got cholesterol affecting exercise, but exercise also affects cholesterol. So the one rule of DAGs is they're not allowed to have any cycles. They're called directed acyclic graphs for a reason. And so obviously something with this dynamic can't be represented by a DAG, not simply. So, we've got all these problems. So let's look at another example. We want to test the causal hypothesis. The housing market always goes up. Therefore, if I invest in the housing market, I'm going to make money. That's a causal conclusion based on that causal assumption. And so here's our data set, and you and I can eyeball this and we know the answer immediately. But does correlational machine learning know the answer immediately? And to do that, we've got to think like a machine, and we've got to say, well, let's divide the time into many slices. So we'll divide it into 1 million slices, and then we'll test all of these data points, and we'll see how many of them support the hypothesis and how many undermine it. And if we have a look and say the housing market always goes up, then we'll find in this example, and we haven't cut the time slices very finely, that 85% of the data points support the hypothesis. And so we've got Homer here thinking, oh, okay, so the longer we have a bull market, the more confident we should be that it's going to keep going up. And of course, you and I know from practical experience that the opposite is true. And so if we rely on correlational machine learning, we run into all of these problems. And I know we've all laughed at these sort of graphs, you know, if it's correlated, it's true. So there's the per capita cheese consumption thing, and that's correlated. So there must be a causal relationship here, or maybe there's a causal relationship here, or maybe there's one here, you know, and so on. And so I think this comic here really sums up the problem of thinking about data naively when it comes to cause. So I'll just pause a few beats for you to take this in. And our champion on the right says, just to be safe, he's going to assume that cancer causes cell phones. Now, we can laugh at this because we know that's not true. But the problem is when we take this logic into domains where we don't already know what's true, and we believe the reports coming out of our machine learning, and we rely on it to make decisions, and of course, we get stupid results because you know, no more sensible than the logic that's being deployed here. And so what are the cumulative consequences of all this? And so we're looking at the model of human decision making, and then all of these human foibles, and then also the foibles of the correlational machine learning techniques that are applied to data to try and overcome the human foibles, which turn out to be just one more human foible. What are the cumulative consequences? And they are that we simply don't know what's going on. We don't know what's going on. We don't understand the relationship between actions we're taking today and the way that the world behaves in the future as a consequence of these actions. And this is why nobody predicted the GFC. It's also why nobody predicted the Trump presidency. You can see Hillary down there at 71.4% to win. And this is Nate Silver's numbers that we're looking at here. And he's, you know, apparently a well-regarded data scientist and predictologist, but he got it wrong this time. And oil prices, who knew that oil was going to go negative? This kind of result would have been absolutely unthinkable when if you had have put this to an econometrician at any point in the past. And so the real question here is, you know, can we do better? Can we do better than collective human reasoning? And of course, the answer is, of course we can, because human reasoning, and particularly when it's collective, is really, you know, leaves a lot to be desired. So this is how Bob Hoffman puts it. He says, we exist in a world of delusions. Our delusions live inside us and cover everything we do. We are so immersed in delusions, we can't even sense that they're there. That's Bob Hoffman. So we've looked at why the conversation about intelligence is so hard to have. We've looked at the Overton window and what's allowed to be discussed and what isn't allowed to be discussed, the way business thinks about AI and intelligence, the way AI community thinks about intelligence, and the way that the most serious problems of the world are currently tackled today, which is that we get groups of people in a room using their flawed cause and effect reasoning to make decisions about the future. And so that's why it's so essential to have this conversation about intelligence. And wouldn't we, of course, prefer to be the grand exception to the rule that people think incorrectly about cause and effect? Imagine if we could be the ones who think correctly about cause and effect and therefore are able to solve all of the so important problems that face humanity, that face us in business, that face us in politics, that face us in medicine, that face us in our personal lives. And so that's how I would introduce the problem. So we understand why the problems are so difficult, complex and challenging, yet so important to solve. We now have slightly clearer picture on what intelligence is, what it isn't, what we'd like it to be, and the state of intelligence today, which is, frankly, could use some improvement. And so this is the setup to now introduce a discussion for what people want to say about intelligence, about the most important problems, and about AI's role in that. Now, of course, we've painted a lot of problems here. In the second part, we're going to look at the solutions to all of these problems through the lens of causal science. So I'll just pause there and hand back to Nadia and Paul so that they can corral some Q&A from the audience.
Yeah, guys, if there's anyone that wants to talk, I guess, how would you like to do it, James? Would you prefer if the questions were asked in the chat, or would you prefer it if someone just asked it outright?
Well, so far we've had a fairly quiet audience. Mm-hmm. And so I think that let's just go with the voice, because I don't think we're going to be overwhelmed.
Agreed.
This is my feeling. And I think so let's start there. And please, cool. I just encourage anyone to understand that these ideas are being put up for debate, and so don't be afraid to challenge them.
And just one final thing is, like, how much time do we have for this mini Q&A before we move on to the next section? Just to let people know, there's going to be another section after this for everyone listening at the moment.
Yeah, so I think we can run about 5 or 10 minutes,
and then go into the next section.
And then we'll go into the next section. Yeah.
And just for anyone that's joined us recently, the next section we're going to be diving into more of the theory. Is that correct, James?
Yeah, that's right. So the next, I'll show you the intro slide for part 2. Mm-hmm. So you guys can all see that, presumably, which is rising to the challenge. So we've just painted the target, and now we're going to talk about how we overcome all these obstacles.
That's part 2. So for part 1, is it free? Is there anything, James? Is there anything you can kind of say as a primer to get people talking? I'm sure there's someone out there that must have a question for James about his presentation.
Yeah. Well, so I can maybe kick them off, because whenever I speak about these topics, the questions I get are very predictable. And so the first one is AGI is an illusion. It doesn't exist. The singularity would kill us all. This is the usual line of questioning at this point. Another one is, what are the ethics of this situation? And I'm on an AI ethics committee, and it's very important that we control this technology. We can't let this run untravelled over our policy-making processes. That's the kind of stuff that I'm used to hearing. So if people want to...
Can I jump in? I've unmuted myself. So I think, yep, great presentation. And there was quite a lot of psychology in there, which is good for the human condition. And we know marketing and etc. have used that model and employ a lot of psychologists to actually sell to people and their psychology. And you've given us a lot of examples about the psychology of what people will believe. So my question is, how do you then technically, develop AI to work that stuff out? Because the approach, and as you've given us lots of examples in this presentation, is it's, you'll believe what's ever on TV, you'll believe what's on the internet, Bloomberg will use certain things, but it's really to capture people's interest, because the psychology attracts them to it, whether it's true or not. And my interest is, so how technically do you develop AI then or through the causal learning or whatever, to work, how do you implement that, rather than, as you said, you got the scientific model for what you know, psychologists have studied for many years and used Jung and all that sort of stuff. And I'm quite interested in Indian philosophy and yoga type of things, which is, you know, like a psychology workbook from an Eastern perspective, which doesn't use the that doesn't use the scientific model. So how should AI in the future be created or developed or configured or whatever, and I'm not a developer, to accurately reflect that psychological condition of humans who are actually going to be using it to solve real world problems?
Well, so there's kind of two parts to the question. And the first one is, how do we understand people? How do we know what they're going to believe? How they reason? When will they believe the news? When won't they believe the news? How do they do their fact checking? When do they do it? All that stuff. And then, having understood the way people behave, how do we make the best decisions in our policy making, etc.? So they're the two questions. To address the first one, what we do is we create models of other intelligences. So one of the primary functions of any higher order intelligence is that it is able to reverse engineer the intelligence of the other intelligences that it deals with. So for example, if we're going to predict the future, we need to understand how people make decisions, because people's decisions will determine the future. And so to drill down on how they make those decisions, we first have to understand their axiology. So axiology is a fancy psychology term.
Yes,
for
I'm
what
familiar with the term. That's okay. Yes.
Yeah. And so then, having mapped their axiology, we then map their ontology. So ontology means we map all of the things that they believe. So some of the things that they believe will be a cultural inheritance. Some of the things they learned at school. Some of the things they learned by doing their own research.
Yes, so again, familiar with the term. So that's what I find really interesting about AI and a lot of what marketing, you know, it's all about psychology. So it's interesting that technology is actually taking on the role of a psychologist as such. So I'm familiar with all of those terms, and what I'm interested in. So it seems like the approach in AI in the past has been, okay, you know, and that's the consultants are psychologists. They're not developers. The psychologists give the goal, and then the developers go for it. So what I'm interested in learning is, okay, so if the approach so far has been backwards, how does this new way of machine learning and causal inference work in this new model that you're proposing?
Yeah, so there's several things to look at. So we saw the list earlier. There's axiology, ontology, semiology, epistemology, morphology, and strategy. There's a long list of things to understand. But if we cut it down to the essentials, the essential ones are axiology, which you already understand, ontology, which is how we represent our knowledge, and then the missing piece here is epistemology. Now, epistemology is the most important part of intelligence, because it tells us that in any given situation, when we should discard our current ontology and replace it with a superior ontology. And by superior, we mean one that represents the real world better. And having represented the real world better, it's now possible for us to construct strategies which better achieve our axiology. And so what causal science is, it is the science of epistemology. And so we'll be looking more in stage 2 about the technical details of what goes on inside that epistemological process. But I think conceptually, just think of epistemology as learning. It means discarding old ontologies and picking up
exactly. Yeah,
ontologies.
And that's what I'm getting. It's like the old, the current approach. I won't say the old approach. The current approach to AI is based on not that, and your framework is to look at the epistemology, and then. So yes, that's.
So most current methods of
AI. Have I muted myself?
most current methods of AI don't have an ontological representation. That's completely missing. Most forms of AI don't have a model-based epistemology. And so these are the deficiencies in current AI. And I think to kind of drill down on this more, we'll do more of that in part 2. But I think the essential part of the procedure is to be able to look at 2 different ontologies and say which one is best.
Cool. Can I just chime in?
Please.
One thing that's interesting about this to me is that I've always been bugged about how the model of game theory has kind of crept into the subconscious and created this idea that there's like always definitive dominant strategies, or you can definitively say that strategies are equal, where in practice, like an organism is operating with a lack of knowledge and has to decide how to interpret the percepts it has to create a model, and then it's kind of trading off between different strategies based on what model it thinks is most likely or something like that. So that's something that sounds very satisfying about this sort of strategy where an AI would be operating with its own ontology.
Yeah, that's it. So imagine this is the usual setup for game theory. So in game theory, you draw up your payoff matrix, and both players can observe the same payoff matrix and calculate it equally. And then based on that, then you can calculate optimal strategies. But the assumption built into game theory is that the payoff matrix represents reality accurately. And I think what your insight is here in this question is that that's never true. Because
yeah, exactly.
And so imagine we've now got 2 competing intelligences. So they're competing in a game theoretic sense. And one of them has a payoff matrix which accurately represents the situation, and the other has an inferior payoff matrix which doesn't accurately represent the situation. It's very clear who's going to win this encounter, which is precisely why superior intelligence dominates in a competitive situation. And so you might be familiar from the game theory literature of a concept called OODA loops. And so OODA loops was introduced by the American military, and it's the concept of, observe, orient, decide, act, and then doing that over and over and over very quickly. And the guy who does that fastest in a dogfight wins the dogfight. And so observe, that one's pretty self-explanatory. Orient is the idea of drawing up your game theory payoff matrix accurately. And then you can decide based on the payoff matrix, make an optimal decision, and then act. And so clearly there's a few dimensions of success here. One of them is being accurate. Well, one of them is having access to observable information. That's important. Another is having enough epistemological strength to draw up the game payoff matrix accurately. And then next is having an optimization algorithm, which is able to run game theory algorithms, and then the ability to act. If any one of those is missing, you're kind of sunk. But if you've got them all, then you're going to win the encounter.
Okay, so just to chime in, we're 10 minutes into the Q&A. So should probably get started on part 2. But just to give you the heads up as well, James, there's some good questions in the Q&A section. I don't know if you want to answer those at the end. Yeah.
Yeah, maybe I'll do an email group answer to written questions. Yeah, and
cool.
then of course, so we'll find other ways to continue this discussion after the podcast. All right, so we'll kick on with part 2. Once again, enormous amount of material, and one of the challenges in presenting this material is that it can get super technical. I've tried to present as much information as I can, which we're going to be able to absorb in the time we've got, which is, less than an hour when we include the discussion portion. So here we go. Let's see how much we can fit in. So I presume my screen's shared again?
Yeah, it's coming through.
Yeah, rising to the challenge. Okay. So here we're introducing the concepts and computation models of causal reasoning. And this is where we'll begin. And so do not adjust your sets. This is what you're supposed to be looking at, this dark screen, because this is how things were once upon a time. And when do I mean? I mean at this time. So this is just at the instant of the Big Bang. And one Planck time after the Big Bang, we see light emerge. And that light is occupying the space of a single Planck length. And the entire mass of the universe is in this single little dot. And it's incredibly dense and it's incredibly explosive. And everything that you and I have ever known is about to be created, or has been created in this instant. And so the universe explodes into existence in this way. And we can measure the time period, and astrophysicists do measure these time periods, and quantum physicists describe all of this. And they can see the universe unfolding. Now, one of the things that you might notice right away is that the universe didn't arise into existence in a uniform way. The universe is lumpy. And so how do we explain that? And this was a problem that stumped physicists for a long time, because in theory, all particles, or whatever word you want to use to describe mass, or in fact mass doesn't actually exist, there's only force that exists. Well, in fact, not even forces exist, there's only fields that exist, and so on. That's a very deep rabbit hole. But whatever it is that exists should be uniformly spread according to the laws of physics that we know. Now, all of this changed when quantum field theory was investigated, hypothesized, as an answer to the question of why is the universe lumpy. And so it turns out that in addition to the electrical fields and the gravitational fields and nuclear fields and so on, forces that we have, we've got the strong and weak nuclear force, we've got the electromagnetic force, we've got the gravitational force, which isn't actually a force because it's actually the curvature of space-time and so on. There were some dimensions missing from this picture, and the important missing component was the quantum fields. And so by adding quantum field theory in, we see that the position of forces is actually uncertain. And it's only when we start to observe these components that they take on actual positions. And so this explains why the universe is lumpy. And these quantum fields continue to operate, and they're operating right now as we sit in our chairs and listen and discuss these topics. Quantum forces are at work, deciding and creating our reality. And so here we are, stars form and everything, and eventually 13.8 billion years later, we've got an Earth. And so how did this happen? And this is the answer. This is the question that physicists turn their minds to. And this is what they've come up with so far. So this is a mathematical equation that describes how we got from the Big Bang to where we are today. Now notice that there's nothing in there about psychology, about free will, and about a lot of the things that we take for granted when we look at strategy or decision making and so on. All that's being described here are the elemental forces. In fact, there's three elemental forces in this equation. Gravity's left out, and that's a good thing because it doesn't actually exist. And this is called the standard model. And it's been described as, or it's known to both physicists as the best set of equations we have to describe the behavior of the universe and everything in it. And so if you want to know what the future looks like, you go to this equation if you're a physicist. And so it hasn't always been this way. The standard model didn't exist. So before Einstein, before Dirac and his equations, before quantum physics, we had special relativity. And so we've got Einstein's equation for general relativity there, and he has a set of equations that describe reality. Now, these don't agree with the Dirac equations, and they don't agree with the standard model. And before special relativity, we had general relativity. And before that, we had Newton's laws. And boy, don't they look simple when we go back to them now, after all of this time, after we've seen where physics has gone in the interim. And so most people on the chat will be familiar with these very basic equations, which most people learn in high school physics. And they're very simple models of how reality unfolds. And so, so simple that you could almost call them cartoonish in their simplicity. And yet, with them, we can do some really useful stuff. And so here we can solve these kinds of problems. And if we hit a golf ball with this much force, we can know exactly the trajectory of its arc. And so let's introduce a new term here, the etiological trajectory. So the etiological trajectory is essentially the computation you make about what the trajectory of the future looks like, or the trajectory of reality as the time arrow increases, given the cause and effect logic of the situation. So that's the etiological trajectory. And so what physics does, what causal science does, what everything should aim to do is calculate an etiological trajectory. Now, if we're in consumer decision making, we'll be using different models of calculation than if we're working in the physics department, or if we're doing interplanetary orbits, or if we're doing heart surgery. All of these fields have got their own equations which describe reality unfolding in the way that makes sense to them and their domain. So it's very much not a one-size-all proposition. Everyone has their own unique models of reality which they use to describe things. And they're not all equally good. So if you stacked two space armies against each other, and one was using Newton's laws and the other was using the standard model, well, the smarter space army is going to prevail in a game theoretic sense because they've got a better representation of reality. So the really fundamental thing to notice about these equations is they appear to us and to many physics students to be causal equations. But are they really? So let's have a look at that more closely. So we would look at this and say, what would happen if force doubled? And most people would look at this and they'd say, well, we know what happens when force doubles. Acceleration doubles. So you hit the golf ball twice as hard, then it accelerates twice as fast and goes twice as far. But its mass doesn't change. That's what a physicist would tell you. But the thing to notice is there's nothing in that equation that tells you that it's the acceleration that changes and not the mass. And so where we have kind of deluded ourselves into thinking that these physical laws are causal equations, we've got to kind of take a step back and say, well, actually, no, they're not causal, they're relational. And we need to do some additional thinking to put them in relational form. So here we see that from time 1 to time 2, the force doesn't necessarily continue. It may do. Our acceleration is a function of what the acceleration was in time 1 and the force divided by the mass. And the mass, of course, doesn't change at all. And so we represent that in these sorts of diagrams. So we're drawing arrows between variables. And so what we're doing is we're moving from the idea of using physics equations to represent reality to learning how to cast these as causal equations. And when we're casting causal equations, what we do is we connect variables which affect other variables in future time periods. So here we've got the Big Bang, and time 0, time 1, time 2, time 3, and this goes off into infinity for 13.8 billion years. And what we find is that the same causal laws play out in every instant. And we know now, because of our study of Planck time, that instant by instant, the world doesn't unfold in a continuous way, it does it in a quantum way. So we're actually stepping, which gives support to the idea that we're all actually living in a simulation. And that's a whole interesting discussion, which we won't pick up now. But there's certainly a lot of support for that idea in physics. And so what it means is, if we've got a start time at time X, which could be yesterday or today, and then we have got access to the mathematics that describe quantum reality and quantum uncertainty and the way it operates on our physical variables, then we're able to then calculate the likely state of the world in time Y. So that's how that works. So that's, in essence, what causal science is figuring out a model of the world so we can use it to adjust the time component in these equations to calculate the future state of the universe. And we do this in the face of quantum uncertainty, and obviously deeper dive to see what that's all about. But all of that is handled in a very elegant way. And I think this here is probably the most famous example of the way we can build a very, very simple causal model which has dramatically powerful properties. And so for those of you who haven't seen a diagram like this before, I'll briefly sketch what it means. So we're interested in our path outside our house, and we want to know why or why not it might be slippery. And we know it gets slippery if it gets wet. And so we see that if it's wet, we've got a causal arrow that makes this slippery. Well, how might it get wet? Well, one way the path could get wet is it might rain. Rain makes the path wet. If the path is wet, that causes it to be slippery. But there's other ways it might get wet. What if somebody turned the sprinkler on? That's another way it could get wet. And then we've got the season. And so if we're in, let's imagine we've got 2 seasons, wet season and dry season, you see it's more likely to rain if we're in the wet season. And then we see this strange arrow here that goes from the season to the sprinkler. How might we explain that? Because surely the sprinkler is an inanimate object, and surely the seasons aren't connected to our sprinkler. And the way we explain it is that the people who set the timer on the sprinkler or who decide when to run the sprinkler know that they've got to run the sprinkler in the dry season, because it's a waste of water to run it in the wet season. And so that's the reason this model contains an arrow from season down to sprinkler, even though in a more elaborate model, we would say that the sprinkler is controlled by the groundskeeper. And then we'd say, well, what controls him, and so on. And we'd go back and back and back. But just using this simple model, let's see what we can wring out of it. So let's imagine we observe that our path is slippery. And we also observe that the season is dry. Now, here's the question. What's the likelihood that it rained? And we say, well, it's not so likely that it rained because the season's dry. It's more likely, therefore, that the reason the path is slippery is because the sprinkler was on. And that's why the path got wet, and therefore it's slippery. And so notice here what we've done is we have used this very, very simple model of reality in the same way we'd use Newton's laws as a model of reality to make observations of our current state and to reason about things that we can't see. In this case, whether or not the sprinkler's on. And then, using our causal knowledge, we know, without observing these variables, that it's more likely that the sprinkler's on than that it rained. And so this is an incredibly powerful thing. And most machine learning models, anything that's not a causal inference model, does not have this power. But it gets better. It gets better because what happens if we observe that the sprinkler is off? So we observe it's dry season, we observe that the path is slippery, we also observe that the sprinkler is off. Now what does that do to our belief about the probability that it rained? And the answer is, our belief in the probability that it rained goes up. And we say, well, this is very curious because the rain doesn't listen to our sprinkler. But when we've observed that it's off, we know that it's more likely that it rained. But does that mean that if we now turn the sprinkler on, it will be less likely that it rained? And so when we ask this question, we see we just have to consult the graph to know that's foolish because the rain doesn't listen to the sprinkler. We know that the rain only listens to the season. And so therefore we know that taking this action has no effect on the probability that it rained. And so this is a way of separating the idea of only observational reasoning into action-based reasoning. And we know that we can affect the state of the world by taking actions and then compute what we call the counterfactual. We can think about things that haven't happened, which might happen. So for example, we can say the sprinkler's off, what if we turned it on? And this is an example of counterfactual reasoning. Would the path still be wet if we turn the sprinkler on? Well, it most certainly would be. But let's imagine the sprinkler was on and we weren't sure if it was raining. What would happen if we turned the sprinkler off? And of course, this simple model can answer all of these questions very intelligently. And had we more time, we could sort of go into how we run the probability theory behind all of this. But in the book of Why, you'll find this all explained very elegantly using a concept called the ladder of causation. So at the first level, we just take observations about reality, and then we use our model to reason about variables we can't see. So that's the level of association. Intervention is when we take that step of saying, well, what if I turn the sprinkler on? Is it now more likely that it rained or less likely? And so this is the interventory step. Or if we wanted our path to be slippery, we could turn the sprinkler on and know we achieve that effect, and we do it by reference to the diagram. And then finally, the step is counterfactual. If we see the sprinklers on and our path is slippery, we can ask ourselves, would the path still have been slippery if we had in the past turned off the sprinkler? And the answer is not certain, but it contains a probability that can be calculated using this model structure. So that's the idea of using a model which is very simple to perform causal reasoning, to reason about states in the future, and to pursue our axiology using our strategy, with the model serving as the ontology. So this is the way all this hangs together. And so the process of epistemology is the process of learning better and better models. So now that we've got some of that terminology under our belts, we can go to actually giving the first definition so far of intelligence. Because notice we haven't defined it yet. So let's do it. What is intelligence? Intelligence is the ability to calculate the best plan to achieve our goals, given the resources and actions available. That's the definition of intelligence. If something's not doing this, then it's not intelligent by this definition. And so how do we measure the strength of intelligence? Well, intelligence increases, or we say it increases, when we can achieve goals which are more and more ambitious. So that is, our axiology becomes more and more ambitious, while our resources and range of action, that is our powers, the actions like turning the sprinkler on and off, while our range of those becomes less and less. And while we are challenged more and more by the forces of complexity, change, uncertainty, misinformation, volatility, and opposition. So that's when all that game theory stuff comes in. Have I got a better ontology than you? Because then I'll win the game. And so all very complex stuff. What's the value? Well, the obvious value of all this is intelligence allows us to achieve goals which are more and more ambitious while our resources and range of action become less and less, and while we're challenged more and more by the forces of complexity, change, uncertainty, volatility, and opposition. And so what could be more valuable than that? And so here's a term that is being bandied about very often in management consulting circles. Everybody's learning now about the VUCA world. So the VUCA world, and I discovered this, I had a chuckle to myself when I saw this template. This is supposed to help you do management consulting or business strategy or something. And it's a template where they point out to you that the world is volatile, uncertain, complex, and ambiguous. And it's up to you to fill in all the boxes using your own intelligence. And so this is quite hilarious because what we'd really like is some help from another intelligence to fill these boxes out for us, and ideally fill them out in a way that's smarter than we could ourselves. And it really offers us no help at all to say, well, you've got to fill these boxes in by yourself. It's like, okay, thanks for nothing. And so let's do an example of intelligence. Let's employ our intelligence. So once again, a very well-known example. But this time we're going to introduce some challenge from the environment, and we're also going to limit our resources so that we're representing a VUCA situation. And so this is actually a real story from the Second World War. And the situation was that armor is very heavy, so you can't put it all over your plane. And in any case, steel's in short supply. But we want to protect our bombers because too many of them are being shot down. But aren't we fortunate? We've got some data scientists, and data scientists are here to do some statistical reasoning about where the armor should go on the planes. And it's very obvious where the armor should go. It should go where the bullets are hitting. Because if we put the armor where the bullets are hitting, then it's going to stop the bullets and the plane stays up. So goes the logic. And those of you who know this story will already be 3 steps ahead of me and know that the decision they took was to put the armor plating everywhere where the bullet holes were not. So these areas here in the middle of the wing, near the cockpit and on the engines that are not struck by bullets in the data collection samples are exactly the places they put the armor. And why did they do that? And a moment's thought will tell you why. Because when they looked at all the bombers returning to base with these bullet holes in them, they realized that these are the bombers that made it home. And all the bombers that were hit in the other places crash landed, didn't make it home, didn't find their way into the data set. And so what we're looking here at is an example of survivorship bias. And so we know that the ones that didn't make it home are the ones that were hit in the petrol tanks, or the ones where the pilots were killed, or the ones that took the engine out. But if it just took a bit of the tail off, or the wingtip, or this central carry area, or the gunner, then the plane could make it back. So let's relate this to causal science. So the way to solve this problem is you must have an ontological model of reality that's sophisticated enough to understand what's going on. And when I say understand, represents all of the actors that make this data pattern that we see in the wings of the plane. And so we've got to at least model the holes in the plane. But more than that, we want to model the planes and the holes and enemies and this concept of a target, because a naive AI might say, well, the way to make sure your bombers come back is fly them out into the Atlantic. Don't fly over Germany. Don't go anywhere near the target and they'll be safe. So, of course, that's not what bombers are for. And so we need to represent this so that doesn't come back as an answer to how do we protect our bombers. And so you see we've got to build out quite a complex model of reality that includes planes, holes, enemies, targets, air resistance, searchlights, the whole gamut, before we know where to put our armor, before we know whether to send our bombers out in the daytime when they can see the target, or the nighttime where they can't see the target, but they also can't be seen by the anti-aircraft gunners. And so this whole thing increases in complexity. So imagine there was a way to represent every possible ontology. So this is kind of, we're getting into mind-blowing territory. Imagine if there was a way mathematically to represent every possible ontology. And then on top of that, not only are we identifying every possible thing that might exist in the world, but we're also able to posit every possible causal relation between all of these things. And then we were able to reason, according to the data we have, about which model of reality is more likely to be true using the evidence. And so this sprinkler system here is one model of reality. It would fit somewhere on this grid. And so this is precisely the way we proceed when we do work in causal science, is we build models. But we've got to have a way of automatically generating models, because otherwise there's too many to build. And so we also need very efficient representation, so we can represent competing models, and if necessary, hundreds of competing models. And then we need a way to keep track of many, many, many elements in the environment. And so this all points to a very complex thing that we need to build. But then once we built all that, then we use trusty old Bayes' rule to decide which model is more likely to be correct given the evidence. So remember we said in game theory, the one who wins is the one with the best ontology, meaning the one who's used Bayes' rule to verify that their ontology is the one that best fits the available semiology. Semiology being the word for the signals that we're able to interpret from the environment. And so this is the mathematics behind causal science. So you need to set up all your model representations, and then you use Bayes' rule to calculate which is more likely to be true given the evidence. And then from there, you can do your moment by moment predictions about what the future looks like given actions you might take. So the point here is that superficial data analysis isn't sufficient. Now, what do I mean by superficial? I mean any data analysis that does not include a model. Now, does deep learning have a model? Does random forest have a model of reality? Does it have planes and searchlights and enemies and targets, or does it just have this superficial description of the data sets, which show us a thin slice of reality, but don't show us the underlying data generating model? And now we're getting into the guts of the difference between causal science and other approaches which are unable to reason with efficacy in the real world that we live in. So what we want to do is we want to take our semiology as represented by the holes in the plane. We want to match that up with a causal ontology, but measure that with Bayes' rules so that the best one floats to the top. And we do that with an effective epistemology. So our effective epistemology here is causal science. That's what we use. Now, psychology's found that people don't build mental models. So this is very interesting because a lot of people assume that people do, but people don't. And so in part one, we looked at all of the biases that people bring to the decision making and the causal reasoning. And this is the information we need to understand why that occurs. It occurs because people don't have models of reality in their head. They've only got biases in their head. That's all they've got. They've got inherited motivations, they've got biological drives, they've got all of those things that we read about in motivation theory. We've got Pavlov's dog and all those kinds of responses, and humans have those too. And so because they're not using an accurate model of reality, they are unable to reason causally and therefore unable to reason about strategy that takes us into the future, particularly in areas that involve complexity and uncertainty and all of those VUCA principles. And so this is the doorway to understanding how a mechanical contraption, a piece of software, can outperform human reasoning. And it can do that by creating a model of reality that looks something like this. So here we might have a look at the effects of drought on suicide. Now, there's no person that can contain this model in their head and do all of the calculations that say, well, you know, what if we lifted employment by this much or dropped it by that much? What's the effect? If drought were to increase by this much or reduce by that much, what would be the effect? And it's those kinds of calculations that humans are very, very poor at doing. And so they bring all their heuristics and their simplifying biases to the table. And these are inevitably wrong. And this is the problem with human reasoning. And the reason why it's so easy for causal science to outperform it. So where's all this stuff being used? You know, it's so good. So the place to take this, of course, is medicine. And so in 2000, nobody had ever heard of it, even though this stuff's been around since the 80s. But by 2015, we're starting to see mention of causal science in the journals of epidemiology. And what we find is there's actually exponential growth of the numbers of mentions of causal science in the epidemiological journals. And so by the time we're hitting 2017, we're getting quotes like this: problems which were previously almost intractable can now be solved relatively easily. So who's this quote coming from? This is coming from medical specialists. This is coming from peer-reviewed medical journals. And so we can trust that we can have confidence that the best specialists with the best and most highly developed ontologies have got to tip their hat to causal science at what it can achieve where their own specialization has struggled for years. And so it's for this reason that you see causal inference winning the prizes that it's won. So it's won the Turing Prize, it's won the Dixon Prize. And it's notable that technologies like deep learning have never had these kinds of accolades. But of course, causal science famously has. And so here's a quote for Judea Pearl that sort of points the way into the future. And this is his advice. And he says, we have to equip machines with a model of the environment. If a machine does not have a model of reality, you cannot expect that machine to behave intelligently in that reality. The first step, one that will take place in maybe 10 years, is that conceptual models of reality will be programmed by humans. The next step will be that machines will postulate such models on their own and will verify and refine them based on empirical evidence. Now, you know the good news about this quote is that it was said 10 years ago. So bang, we're here and we're doing it. And so this is where we introduce Sky, which is software that delivers on that promise. And so yeah, there's a little trailer here. I don't think the sound's coming through, but that's okay. There's some visuals which kind of give the flavor of what this next revolution in artificial intelligence is really about. So that's the promo piece for this technology. And it's a shame you didn't hear the dramatic background music, but it was all very exciting. But let's have a look at really what's under the hood here. Like what are we dealing with? And what Sky really is, it facilitates intelligent reasoning when faced with problems involving uncertainty. So that's really what it's for. And so this is the use to which causal science is put. And so after appropriate modeling and training, so notice the part after appropriate modeling, we've seen the importance of the modeling step. Sky's got the potential to be superior to both human reasoning and any form of correlational machine learning, which is what we want. And because it makes it an excellent choice as an engine to support financial trading or policy analysis or medical diagnosis or marketing or whatever you want to turn it to. Now, we know all models are wrong. They're always a simplification of reality. But just in the same way as Newton's laws were a simplification of reality, but yet were still incredibly useful, just in the same way that the simple sprinkler model, although it's a very elementary combination of 8 nodes, it was still able to supply to us a surprising amount of causal information. In the same way, even our simple models are very useful. And so it's a learning machine. It's able to a degree, construct new models. And so this is how it learns automatically. It doesn't claim to predict the future perfectly because it's only as good as its best models. And so there's always an ongoing background process to improve, to do model improvement. But we can certainly have confidence that it's going to give better predictions than other approaches that don't even include any model. And so that would include things like deep learning and regression, and all of the usual techniques that are being deployed. So it's based on Judea Pearl's work. It has been, elements of the technology have been licensed by some large players. One of them is NEC, and you might know them as the manufacturer of the world's fastest supercomputers. And they're also entering the quantum realm. And Causal Science, as you've seen, is a very good fit for quantum science. So when we get quantum computing, the Causal Science algorithms are going to overlay on top of the quantum computing hardware like a hand in a glove. And we're able to compute efficiently all of the ontologies, all the possible causal relations, and then create our predictions. So what's inside? Well, models of everything. So we've got models of banks or people or stock prices and all the things that we care about. And if you're going to apply this in a medical context, then you'd have models of patients and hearts and defibrillators and nurses, schedules, and all of that stuff. And the objects inside the system have attributes, which then we can track. So we can say, well, how is this person how's his life journey, his customer journey transpiring? And so he's born, he graduates, he buys a house, he travels. And we track all of the nodes. So notice his name doesn't change over the course of his life, but something like his age does. Now his age changes in a very predictable way, but where he holidays changes less predictably. Then there's the model of car he chooses to buy, or which way he votes. But all of these things are addressable through the lens of causal science, and that's what this is all about. Now, Sky's able to do this even for things that haven't happened yet. And so this is incredibly exciting because it means that we can then, if we're a marketer, for example, we can market toward consumer preferences as they are emerging, as they will emerge, rather than as they've been seen in the rearview mirror. So one of the basic fundamental drawbacks of most data science approaches is they're always a rear mirror view of reality, always looking at what has been, making the assumption that the future will be like the past. But of course, this is a fatal assumption because it's never been true that the future is like the past. And so all of the machine learning models that don't include modeling as an element of their computation are subject to that flaw. They embody that flaw. But of course, causal science has got the ability to predict futures which don't appear in the training data set. And so this is tremendously exciting for anybody in the innovation space. Say, for example, you want to do clean energy, or you want to introduce new political ideas or solutions. Or you want to combat a virus that's never appeared before, then you need the ability to reason about futures which have never existed. And so how does this all hang together in an architectural sense? Well, Sky is connected to the Internet of Things, and then there's a code API that you use to access the intelligence. And then other intelligent applications can access through the code API. And you can also build user interfaces to it. And these user interfaces can be graphical, but they might also be voice. So then you'd be able to talk to it. And so a lot of the work done for sort of Siri and Alexa and all that stuff would plug in this way. Wolfram Alpha is one of the data sources it currently uses. I've been in discussion with guys like Cognino on having Sky become the engine for the kind of reasoning they do about stock prediction and so on. And so what does a methodology look like for working with Sky? So how do you work collaboratively with it? Well, this is sort of the cycle. You start with your current knowledge, your current ontology, and then you improve it. And then you simulate the implications, and now we're able to make better decisions. So that's how simply it hangs together. So the improving our knowledge through AI, that's the whole causal science piece. This is where we get the term scientific knowledge from. And the simulated kinetics, which is the other way to read the SKY acronym, simulated kinetics through artificial intelligence, is when we run our models forward in a simulation to say, well, if it is true that the world acts according to our model, here's what the future looks like. Now, of course, we don't only consider one model. We're not, so simplistic a simulation environment that we say, oh, well, we know the model is this, that we know what the model is, we'll assume it's this one and let's see the future. No, we consider many, many models simultaneously and we apportion uncertainty across all of them to arrive at a blended picture of the most likely future reality. So modeling requires a language for knowledge representation. So Sky has its own language for knowledge representation. So when we have an ontology, we've now got a way to define it. And then it's got a learning loop, which is causal science, where we know how to update the ontologies. So update our knowledge representations. And we use the algorithms of causal science here. And then it's got a simulation component. So then it can run complex simulations that involve many, many parts and components. It's got background knowledge that we can draw on in these simulations. And so then we're able to see what the future looks like and make our predictions. And this can be true under intervention. So we can say, what if we took this action or that action? And then we can run our simulation again and find out what the answer is. And then knowing what those answers are, we can make better decisions. So that's the final step, where we capture the value. And so remember our definition of intelligence earlier? We talked about the ability to plan how to capture value in the face of uncertainty and all of these things, and complexity and adversity and all of these things. Well, this is all captured in the Sky methodology. And so what we're looking at is a picture of intelligence. And the faster we run this, the faster we're running our OODA loop. And this is the way we get competitive. We get competitive in business, we get competitive in politics, we get smarter in econometrics, we get more effective at medicine, or whatever our chosen domain is. And so initially when you work with Sky, the models are insanely simple. And they have very elementary behavior. But what's surprising is they quickly outstrip the kinds of computations that a human can make, and certainly that a human can make with any accuracy or with any acknowledgement of the underlying complexities and uncertainties. So it's very difficult, for example, for a human to calculate futures where there are several potential models that might be true. And to keep track of all that information is very difficult for a person. And so, what we see emerge time and again in the world of AI is things start off in a very elementary way, but quickly exceed human performance. And so this is the causal resolution that I and others are working to achieve with tools like Sky and other tools. And so the picture becomes not just one of collective human intelligence, but human intelligence combined or augmented with these artificially intelligent beings that sit within our midst and that we can interrogate and talk to through interfaces. And Sky is one of these, but there'll be others. OpenAI is working on theirs, Microsoft's working on theirs, there's the distributed AI group that has got several people working on this challenge. And you too can also enter this picture and build an artificial intelligence that works causally and participates in this discussion. But what I anticipate and others anticipate is that we'll quickly come to a position where these machines will be so much better at reasoning about cause and effect, and therefore reasoning about the future, reasoning about strategy and game theory and so on, that there'll be no point in humans being involved in the chain. That the humans will be the weak link in the chain, and the system will perform better without them there. And this is a very frightening picture for a lot of people. And they say, we've got to stop this happening because humans are essential. And, you know, we need to inject human reasoning because without that, something. And they kind of fall down on that point because we really have to ask anyone making this argument about what the real value is of keeping humans involved in the decision loop. And usually it comes down to some form of ethical oversight, and that bad outcomes will happen. And then the question becomes, well, who is the judge? Who is the better judge of what the outcome will be of any action? And would we use the weakest link in the chain to decide what is ethical if our ethics are all about taking the best ethical action where best is defined by the actual outcome? And what we'll find is that actually it's the AI that's in a much better position than the people to behave ethically if what we care about is outcomes. And so this is a very important point. Obviously, a longer discussion. We don't have time to get into the ethics of AI today because we're trying to do a more technical thing. But what is envisaged is that this will be the relationship between people and machines. We're going to have AI learning, improving the models, and it will be the people who come along to this machine with their own axiology, their own value system. So the AI doesn't tell them what to value. It just tells them what to do to get what they value. And so that's simulating the implications of actions they might take, and then helping the people to make better decisions. So this whole system runs for the benefit of people. So that's a very important point here. AI is not in control of the decision making. Notice that. The people in control of the decision making. What the machine's in charge of is accurate causal reasoning. And so this is the way that there can be a harmonious conjoining of people and machine. And so we've seen this before. We know what this picture looks like. People who took on tractors became more productive and had better standards of living. People who took on in-home appliances like washing machines and dryers and microwaves have a better standard of living. People who take on computers and information technology and therefore become an order of magnitude more productive have a better standard of living. And it's going to be like this with artificial intelligence. The people who take on artificial intelligence are going to be the ones with the highest standard of living. To the point where it's going to be possible in many cases to develop a lot of the production of wealth decisions to machines, and even the distribution decisions, under the guidance of, appropriate human ideologies and so on. Another deep discussion. But essentially, there won't be a need for people to work, because decisions about production decisions, and the molding of reality to suit human needs can be placed in the hands of machines, because they're the ones who know how to reason about cause and effect most appropriately. And so, where to now? What do we do? What do we do with all this? Well, here's some suggestions. One is to get a new picture in your mind of what the future looks like. And it's building true intelligence with a causal science underpinning, such as software like Sky, such as what's coming out of the Microsoft research on artificial general intelligence. And to encourage the use of this by policymakers, by econometricians, by governments, by clean energy advocates, by social policymakers, by doctors, to encourage it so that we all get better futures. We get healed patients, we get cheaper energy, we get all the benefits. And as members of the data science community, which I assume most of you are, this is the place to connect. This is the technology to learn. This is the place to be if you're seeing your own career unfold over the next decade or two. And so what will the impacts be? Well, the plan is to take this technology into government, to take it into the altruism movement, to take it into the energy movement in every area of industry. And I know all of the people on this call are from all of these places. And so I would encourage you to reach out and continue the discussion about how you personally can access this technology to make better decisions in the context that you are currently operating in. So thank you very much. I've used the full hour, and so, but I still would like, if we can, to run some discussion. I think Nadia said earlier that we can be a little bit flexible on time, and I would like to give everybody the opportunity to ask questions, because I know we've presented a lot of material, and no doubt there's going to be a lot of thoughts. So I'll hand it back to you, Nadia and Paul, to once again organise the discussion.
Nadia, do you think it's a good time to just show your slides?
Yeah, I might jump in and just show a couple of the upcoming reactor events that we do have. James, that might give you an opportunity just to take a look in the chat as well. I do know there's a couple of questions in there from the last session.
Some really good ones.
Yeah, I will just jump in and share my screen with you all. Well, it gives you an opportunity to do that, James. So, hi everyone. For those who don't know me, my name is Nadia. I am the Community Engagement and Events Manager for the Reactor in Sydney. So I just want to let you know that we do have a lot of good upcoming events at the Microsoft Reactor, and you can find this out on our meetup page. So it's meetup.com/Microsoft Reactor Sydney. And you can also see quite a few updates on our Twitter page as well, which is at MSFT Reactor. So you won't just see Sydney events, you'll also see a couple of global events that we have as well. And every Tuesday we've been running 2-hour workshops around Python, AI, machine learning, and we're starting to do one around a blockchain fundamentals as well. So next week we've got a session on build your own virtual assistant in Teams using Azure AI. So this is done by one of our community influencers, Ashish, who ran a session this week, if you may have seen it. So he's going to teach you how to enhance your Teams experience. Another big event that's coming up for Microsoft next week on May 20 and 21st is Microsoft Build 2020. So this event is for developers by developers. So you'll have a lot of sessions from not only Sydney, but globally. So you can register at mybuild.microsoft.com, and it's an absolutely free event. The last one I thought that was quite interesting that we'll be hosting is called Charting a Virus, COVID-19 in New Zealand. So I'm working with one of our Microsoft MVPs who actually took all this data from the official government website and put it together in Power BI as well. So she'll teach you how to do Excel, Power BI with your data, and take you through a couple of the challenges that she went through as well. So again, here's our information on our meetup page and our Twitter. So join our community, and yeah, so I'm going to hand it back over to you, James, so you can answer some of the questions.
Okay, great. Thank you, Nadia. I was just starting to furiously type, but it's going to be much easier to speak.
Yeah.
These answers. So I'm just sort of reading them most recent to so last first, just because that's the way my scrolling is working. And the first one was find that again. Can this new way of AI using epistemology be done with conventional computers, or do we need quantum to evolve first? The answer is actually causal science, the way all this is hanging together, is less computationally expensive than something like deep learning. And so I know that there's a big push on right now to press graphical GPUs into the service of deep learning kits, and we're trying to optimize TensorFlow, and we're trying to build supercomputers that can run deep learning faster. And I know that deep learning training times are horrendously big. This is not the picture at all in causal science. Causal science is incredibly fast and efficient and cheap relative to, say, deep learning. And the reason is that it represents causal futural knowledge functionally. And so in the same way as it's easy to just compute a function ahead, once let's say we're doing integration or calculus, and we can pick an arbitrary, and we've integrated over t, which is our integral. And so that means we can now, if we've got an integral function representing t, we can ask what the value of t is in any future time period just using mathematical functions without having to do entire simulations of that step. And so using those kinds of efficiencies, we make the whole thing of modeling reality much more efficient. So another simple question, does intelligence fit in with the DIKW pyramid, the equivalent to wisdom? So whoever asked that question, could you please elaborate on the DIKW pyramid?
Yeah, that's data, information, knowledge, wisdom. So it's the just the hierarchy starting from data, working your way up, information, knowledge, then wisdom.
Oh, okay. All right, sure. So that's just a way of classifying information, or, you know, if we're looking at something, how useful is it? And we set this hierarchy up. So here's the way I would say this maps to the causal science world. We've got the concept in causal science of semiology. Semiology represents all of the data sources that you have access to. Now, bear in mind, a lot of that might be lies. It might be fake. It might be other intelligences trying to deceive you. So when we say it's our semiology, we certainly don't mean we believe it. So don't make that mistake. But all of that would correspond with data. That's the raw material we have to reason about reality. And see, one of the things we can put in our model is the idea that we have an opponent and that our opponent might be deceiving us. And so if we, for example, have a functional ontology, we're pretty happy with it, and we get some data that we can use, then that becomes useful. So let's call that information. Now, an example I saw on LinkedIn recently was the bathroom test. So apparently a good way to gauge how what a company culture's like is you go into the executive bathrooms and you go into the staff bathrooms and you look at the difference. And the bigger the difference is between the executive bathroom and the staff bathroom, the more dysfunctional the culture in that company. And so the semiology, just recording how clean each environment is, how many cubicles there are, how much hand sanitizer, how soft the towels are, that's the semiology. But once you've grabbed that data, because we can relate it to something we care about, which is that we want to measure the cultural toxicity of the environment, or otherwise the health of the environment, because we can use it, then that semiology then becomes information. And we feed it into our ontology to draw conclusions. The knowledge is the model itself. So knowing our model, we know how to map semiology to information. And so we know which data to go out and look for. One of the weaknesses of the big data paradigm was the idea was go out and collect everything you can and worry about what to do with it later. And this is extraordinarily inefficient. But when you have a functional ontology, you can be very precise with knowing what information you want to collect. And so the information that you actually collect can be 1/100th of the information you would under a big data paradigm. And so in this way, we can dramatically reduce our need for data by having a superior knowledge structure. Now, wisdom is the final piece. This is advice on how to choose our axiology. So, for an example, I was having a discussion the other day with someone and they said, we really want, more female representation in the boardroom. And then when that was achieved in a certain environment, then it sort of shifted. It's like, well, actually, we want to make a difference. So we're there, but we're just observers. And what we really want to do is change the outcomes. We want to have influence. And so then they went on with that model for a while. But then I put it to them that what if the executive structure that was currently there was going to make a decision that you would have agreed with anyway? And we've set our model up to give you maximum influence. Does that mean you now need to disagree with propositions that you formerly would have agreed with just to have influence? Because once we've set influence up as your axiology, we go chasing that to the detriment of what you really want. And what you really want is for decisions to be made the way you'd like to, in which case it's not really actually necessary for you to have influence anymore. And so you see how the axiology evolves. And the evolution of axiology is what I term wisdom. So I think there are very clear mappings between causal science and the way we think about things and the DIKW pyramid as you've represented it here. So yeah, just scrolling back through the comments. So for example, in the stock market, people seek to maximize profit or entropy never decreases. And so I'd say, yes, people do seek to maximize profit, and they could do so much more efficiently and much more reliably with a more efficacious causal science than the way that hedge funds and treasuries currently make decisions about their portfolios of stocks and other assets. And in fact, this is one of the most active areas of my company, Epistemology, is to give advice to portfolio managers about how to better read the future so they can do better stock allocation. So good call out. So are there non-causal explanations? Why do explanations have to be causal? Well, so this is a question that goes to beyond physics to metaphysics, and let's take a look at our definition of cause and see why it might be a useful concept. So our definition of cause is if the cause happens, then the effect will always happen. That's the definition of cause. So it always happens. It always happened in the past. It will happen now. If we do it now, in the future it will happen. This is why it makes itself a reliable basis for prediction, because of this always property that it has. And is this concept useful? Why do explanations have to be causal? Well, and the answer is because causal is useful. I mean, imagine that we were using some other concept apart from cause that didn't have this property of reliability. Then we have no firm basis for prediction. And so what we have we've got something that's grounded in scientific thinking. It's got all the rigor of Karl Popper. It's got all the support of mathematics. It has a clear definition, and it's absolutely reliable. So no, we don't have to use it. We can use astrology. We can use, reinforcement learning. We can use deep learning. We can use other methods, but will they serve us as well is the real question. And in my opinion, other methods don't serve us as well when we care about better futures. So we've got a question here. Would it not be true that very simple rules in physical processes acting on massive scale often determine outcomes? Absolutely. So if you've got individual voters and you poll them in a polling booth, you take a sample, as was done for the 2016 elections, you might find out that most people in the room are going to vote Democrat. But then come election day, it turned out most of them voted Republican. And so it was the mass that determined the outcome in that particular instance. So yes, it's absolutely true that we need to think in terms of aggregates, population aggregates. We can't think in terms of individuals in isolation. And I think you're also thinking there of physical systems. So the gravitational force only exists where there's mass, and if the physical object is small enough, then it has no mass, and therefore it doesn't have gravity, and it's not subject to gravity fields. Therefore, it's got a different relationship with time, and so on. So that's certainly all true. And okay, just searching back for more questions. Oh, we've got some technical advice here, which I wish I'd read sooner. When you share in Teams, you need to tick include system audio. Okay, that's something for me next time. And so what, I presume that was the shell scenarios clip that I guess we're referring to. Okay, is Sky an organization or a system library? Okay, so Sky is a software product. It's a set of Python libraries. I'm the developer of these Python libraries. And to access Sky, you do that through my consulting business. My consulting business is called epistemology. And so we've spoken today about the important role that epistemology plays in causal science. I think it's the most important component, the one where we decide to replace our existing ontology with a superior ontology. That's why the company is called epistemology. And Sky is a product offered by epistemology. So it's sold as a consulting service. That's the way it exists. So if you wanted to talk more about, how to access it or look at it or demo it, or then just reach out via email or LinkedIn. New joiners and okay, somebody's saying they've got a clearer concept now, which is fantastic. I think the sprinkler example is a really good way to clarify a lot of the mystification about how very simple models can produce such powerful results. And that was the other reference. There's the Book of Why. So the Book of Why is an excellent beginning place. And I think we are almost back to the beginning. So if anybody has additional questions, I'd be very happy to take them now in the chat. Or if you'd like some one-on-one time, then please do reach out on LinkedIn or through email, and I'd be very happy to talk one-on-one about anything you're interested in, whether it's using superior intelligence or learning how to be a causal data scientist or intelligence or architectures or anything that you might be interested in.
Okay, I'm just going to interrupt again. Sorry, everybody. I put all my questions in the chat function in the team rather than the official Q&A, which I'm not sure if they're being read or not, but there's quite a few questions in there, just in the chat section of the presentation. So I'm going to jump in and ask my question. So as I said, I'm not a developer. I'm more of a decision maker in my organization, and we're looking at AI. And my takeaway from this, and I'd like to be corrected if I'm wrong, but as we know, there's like a technical solution to everything as long as the goal and the business objective is set. There's a technical way around all of that, but to assist in the technical or to give developers or people that are actually implementing the AI solutions, is my takeaway from this presentation is that rather than using the existing APIs and libraries that are out there that have not used this causal inference methodology, which it seems like Sky is taking a different approach to everything else. So it's the advantage of Sky, if it's being put out there, is that our developers should actually like subscribe or whatever to these libraries, because the data is a much better indication of what people actually need, and they should be developing using that to obtain better outcomes. That's my takeaway, but I could be incorrect in saying that. I don't know. As I said, I'm not a developer, but I'm more of a decision maker, because we've talked a lot about, the psychology of people and, people being important, blah, blah, blah. But the approach of Sky seems to be in the way that they get their methodology and framework of how they get their data is a different approach to any of the other AI offerings out there.
Absolutely. It's absolutely a different approach. And if I could put my finger on the primary difference, is that one approach, the Sky approach, models all of reality conceptually. So we've got to build it a bit at a time, but that's the goal of it. And the other approaches work with data on hand. So let me just do a compare and contrast. So if you're in a marketing function, this is very typical. We go through the CRM system and we look at past transactions and we look at all the customer journeys of everyone who's ever bought our product or visited our website. And then information, so know your customer projects are run based on knowledge that's in our CRM system and in our transactional database. So banks do this all the time, for example, and insurance companies do this all the time. This is the most common way. People suck their data out of their ERP system, they throw it into Tableau, they put up some graphs, and there's know your customer. Now, here's the problem with this approach. What you're looking at are the customers you've already got, but you've already got those customers. If you're a marketer, you're interested in the customers you don't have, the ones that didn't visit your website. And so
yes,
that's why,
yeah, exactly. That's what your presentation has shown me. Is just like, look, you're using a different model, and that's the difference.
Just to chime in here, this is the last question. We're already 20 minutes over time. So
okay. I just say too, there's a lot of questions in the meeting chat. I don't know if they've been answered.
Yeah,
I'll shut up now.
Sorry, Tiffany. We're just gonna wrap it up after this. Cheers.
okay, good. Well, thanks so much, everybody, for attending, and thank you, Paul and Nadia, for hosting. And I look forward to, to interacting with you, all you guys, further.
Cool. Cheers, guys.
Thank you, James.
Yeah.
It's been great. Thanks,
Thank you,
everyone. We'll be in touch. Bye.
Okay, bye for now.